Sorry, I forgot to record the first 5 minutes. But when you graph this function, y equals x over e to the x, and trace it out to the right, do your y's seem to be approaching some limit? Some weird different. You want to see if I can see what that is? Ooh. Okay, that's interesting. Some weird different kind of plot. Zoom and see if 6 fixes it. No, it's doing box plots from statistics.
Oh.
Okay, so how do we clear that? Stat. And then it does a parabola on top of that. No, it's not a parabola. It is the graph. It just has a box plot in the background. So clear. It's what clears? Let me see. Second draw. Clear draw number 1. Oh, it erased the function, but not the box plot. We might have to Google to figure out how to get rid of that box plot. Check one more thing. Second plus 712. What is that? Really? Okay. Okay. Oh, here's something else. Points. I'm not sure, but I thought clear draw was going to do it, and it erased the function instead of the box plot. But if you Google how to get rid of box plot onto a TI-83, you'll get an answer quickly. Just glancing, glancing at Emma's function with the box plot in the background, I do think I could tell what the limit was. As x was going forever to the right, what did your y seem to be approaching? Yeah, it looks like it's getting closer and closer to the x-axis as y goes to infinity. So sometimes 0 times infinity is 0. And then what about graphing e to the x over x and seeing what that limit is as x goes to infinity? What appears to be happening as x goes forever to the right? It's taken off. Sometimes 0 times infinity is infinity. And really, we could have looked at these two, even though we didn't have an analytical way of doing it. We know that exponential functions get big faster than linear functions. Yes? Are you with me? All right. So this third one was linear over exponential. It's a fraction that's denominator is getting big a lot faster than its numerator. So it makes sense that's going to 0. And this one, we have an exponential over a linear. Exponential is getting big a lot faster, so it makes sense that that goes to infinity. All right, so 4 different times we got 0 times infinity by direct substitution, but then when we resolved that or figured out the limit some other way, we got 4 different answers. So what is 0 times infinity? Is it 1? Is it 2? Is it 0? Is it infinity? Is it something else? I don't know. That's the definition of indeterminate form. All right. Like I said, in section 2.3, we learned some tools for resolving indeterminate form. L'Hopital's rule is just a different tool for resolving indeterminate form that uses derivatives. So we couldn't have used L'Hopital in section 2.3 because we didn't know how to find a derivative yet. L'Hopital's rule states that under certain conditions, and we have to verify the conditions. We can't just use L'Hopital's rule whenever we feel like it. We have to verify that the conditions are met. But when the conditions are met, then the limit of the quotient, the fraction, f of x over g of x, can be determined by finding the limit of the quotient of the derivatives. So we have some f of x over g of x. We can't find its limit, so we're going to find the limit of the derivative of the numerator, derivative of the denominator. That's L'Hopital's rule. So what are the conditions? Well, f and g have to be differentiable on some open interval AB containing c, except for possibly at c itself. C is the number in the conclusion down here. C is the number that x is approaching. So whatever that c is, f and g have to be differentiable on an open interval containing c, except for possibly at c itself. What does it mean to be differential? What cannot happen in some interval around A and B, or interval around C? What makes something not differentiable? Discontinuities, actually non-removable discontinuities. If there's a hole in the graph, that's not a problem. We could just fill in the hole and we've removed the discontinuity. But if there's a gap, then we can't fix that, and that's a non-removable discontinuity. That makes something non-differentiable. Can you think of something else? Ooh, infinitely many oscillations. Near as you approach some value C, the graph just goes nuts like the EKG of somebody having a heart attack. And then there's one other thing that we recognize on a graph that the function's not going to be differentiable here. Graph of y equals absolute value of x is not differentiable at 0 because it has a sharp turning point. The slope of the line changes at 0. It's negative 1 coming from the left. It's positive 1 coming from the right. So, but if f and g are differentiable on some open interval AB containing C, except for there could possibly be a hole in the graph at C, and that's okay. If the derivative is not 0 for all the x's in AB, because the derivative of g of x is going to end up in the denominator, and we know we can't have 0 in the denominator. If the limit as x goes to c of f of x over gx produces either 0 over 0 or plus or minus infinity over plus or minus infinity. In other words, L'Hopital's rule is only going to work for these two scenarios. It wouldn't have helped us up here because we didn't have 0 over 0. We didn't have infinity over infinity. So we're still going to have some indeterminate forms that can't be resolved even by L'Hopital's rule. And if this limit exists, if these four conditions exist, then the limit as x goes to c of f of x over g of x is the same thing as the limit as x goes to c of f prime of x over g prime of x. And you think, that could be significantly difficult if I have to take the derivative of the numerator and the derivative of the denominator and then find that limit. That would seem much harder than just finding the limit of the original function. Well, except for the limit of the original function is in determinate form. You can't find it. By direct substitution, you either get 0 over 0 or infinity over infinity. That's when you can use L'Hopital's rule. Important notes. If I just said r of x, and r stands for some rational function, if r of x equals f of x over g of x, and I wanted to find r prime, Would the way to find r prime be just take the derivative of the numerator, derivative of the denominator? Oh, that would take the quotient rule. The way we would find r prime is the quotient rule. So L'Hopital's rule is not the quotient rule. In the quotient rule, we don't just take the derivative of the numerator, derivative of the denominator. L'Hopital's rule may be used for one-sided limits. The limit as x approaches c from the left or from the right, and for limits at infinity, as x goes to positive infinity or negative infinity. You may need to review the guidelines for finding limits at infinity of rational functions, but I bet you remember them. It was just that theorem on horizontal asymptotes. You look at the degree of the numerator, degree of the denominator. If the degree of the numerator is less than the degree of the denominator, if the bottom's getting big faster than the top, what's the whole thing going to? 0. Or if you have a rational function where the degree of the numerator is the same as the degree of the denominator, how do you get that horizontal asymptote? Ratio of the leading coefficients. And if the degree of the numerator is higher than the degree of the denominator, what do you know about the horizontal asymptote? There's not one. It takes off to infinity. So that is what's on page 242. You may not even need to look at it. And third important note, L'Hopital's rule. I'd actually like to hear a French person say that, because I have a feeling, if a French person said it, it wouldn't sound like L'Hopital's rule. Yeah, I went, oh, that's German. Really spoken. You can only use it to resolve 0 over 0 or plus or minus infinity over plus or minus infinity. It would not have helped us at all up here with 0 times infinity. So know when you can use it and when you can't use it. All right. We'll look at these evens, and then your homework is 7 through 41. So, and that's all we need to do today. Just look at some of the even problems from number 7 to 41. I thought I circled. Oh, I know where I circled them. Okay. I know. Why are we? Yeah. Well, right. I hate to make this on tape. I am literally 12 hours ahead of the class now because we have caught up with what I had prepared before. But I know 8.8 is improper integrals, and I think we use L'Hopital's rule for improper integrals. I'm not sure of that because I'm only 12 hours ahead. I'm now 3 weeks ahead of statistics and 12 hours ahead of calculus. That's okay. Christmas is coming. Let me just mention a few things about the first one. The first one we'll write down as number 12, but number 8, just pointing at it for a second. Can you evaluate that limit by direct substitution? No. You'll get 0 in the denominator. What if you let x be negative 4 in the numerator? That'd be 32 minus 52 is negative 20 plus 20. Oh, that would give me 0 over 0. So there's a chance that I can use L'Hopital's rule. Is 2x squared plus 13x plus 20 differentiable on an open interval around negative 4? It's a polynomial. It's continuous everywhere. It's differentiable everywhere. Same thing in the numerator, or in the denominator. It's differentiable. Got to peek at my other conditions. Oh, the denominator won't be 0. The derivative of the denominator won't be 0 in an interval around negative 4. That's condition number 2. Condition number 3, we've already seen that it gives us a indeterminate form that L'Hopital's rule helps with. It would give us 0 over 0. So the directions for 1 through 13 say, do this like you would have done it in 2.3, and then do it with L'Hopital's rule to show you get the same answer, and L'Hopital's rule actually works. Now, what we would have done in 2.3 is we would have factored out that numerator, and it would have turned out that the x plus 4s would cancel, and then we could evaluate it by direct substitution. If we take the derivative of the numerator, hey, what is the derivative of the numerator? 4x plus 13, and the derivative of the denominator is 1. So if we plug negative 4 into 4x plus 13, we would get the same answer as if we factored the numerator, canceled the common factors, and did it by direct substitution. Let me just mention that in number 10, can you remember the 3 tools for resolving indeterminate form that we just mentioned? Which one of those tools might fix that problem? Multiplying by the conjugate of the numerator. So our 2.3 way of doing things on number 8 is simplify the fraction. On number 10, it's multiply numerator and denominator by the conjugate. Number 12, I just wonder if you remember that little guy. We had a way of dealing with that in 2.3. I think that was something that we used when we had inverse trig functions. We could change them into algebraic. I just suddenly had a Michaela Van Landingham pain because we had two special limits in 2.3. The limit as x goes to 0 of sine x over x was one of them, and the other was the limit as x goes to 0, and I don't even remember what this one was. I'd have to re-memorize it. But this answer, I remember, turned out to be 1, and this answer turned out to be 0, and I believe it was Michaela when I said I can never remember which one is 1 and which one is 0. I think it was Michaela that said, well, that I in sine looks like a 1. And this one had a cosine in it, and she said, well, it has an O in it. Well, that's going to work for the rest of my life. Okay, so that was a little aside, except for to say that we have this special limit if this ugly is the same as the ugly in the denominator, the limit of that as x goes to 0 is 1. The problem is we don't have the same thing in the denominator that we have for the argument of sine. How can we legally do that? How can we make this become, I think it's the first time I said, write down what you want and figure out a legal way to get it. Here's what I want, but that's not equivalent to the line above it. Well, I could make it equivalent to the line above it. Make the 6 become a 4. Or what can make a 4? If I multiplied it by 2/3, I'm writing real tiny in case I have to write over it. That would be 1/9, not 4. Maybe it's 3/2. Then I would have 3/12. Ooh, 3/12 is 4. So you figured it out. If I multiply that expression by 3 over 2, and then I check to make sure it's equivalent to the line above it, It is, because 3 goes into 6 2 times, and 2 times 2 is 4. We have a theorem that says the limit of a constant times a function is just the constant times the limit of the function, and the limit of that function is 1, so that's 3 halves. Hey, what would you say if you were tutoring something? Bless you. If you were tutoring someone and they got really upset and said, but you can't just go around multiplying things by 3 halves whenever you want to. Whatever you multiply the numerator by, you've got to multiply the denominator by the same thing. What would you say to that person? Oh, Miss, you are not getting my recommendation if you're going to be telling frustrated math students to be quiet. I know.
You weren't modifying the original but you wanted to make it equal.
Yes, I didn't just take that fraction and multiply it by 3 halves. I actually took that fraction and multiplied it by, well, no, I actually multiplied it.
As long as you're getting the original, you have to make sure it's equivalent to the other.
Yeah. I multiplied it both by 3 halves and 2/3, which is actually 1. Here's where I multiplied it by 3 halves. Here's where I multiplied it by 2/3. Yeah, just over and over, say, make sure that it's equivalent to the line above it. And folks who are used to doing lots of things in their head don't have that habit yet. Well, it's so important. Or down the page, make sure everyone is equivalent to the line above it. All right, so 7 through 14, we could do that using some method, some tool in our toolbox from section 2.3, and then we can do it by L'Hopital's rule and show that we get the same answer both ways. And then 15 through 41, just say, forget all the tools that you knew in 2.3 and do it by L'Hopital's rule. I'm not even going to follow those directions perfectly because I don't believe in doing easy things the hard way. If I can look at it, for example, number 28, the limit as x goes to infinity. If the numerator is a higher degree than the denominator and my x's are getting infinitely big, what do I know that limit is? Yeah, I know it doesn't exist, and the reason it doesn't exist is it's going to infinity. So I know the answer to 28 is infinity. I'm just going to write that down. All right? You don't have to use L'Hopital's rule on anything that you can figure out some other way. But number 20, I'm not sure that I could figure that out a different way. Hey, why don't I just say the degree of the numerator is higher than the degree of the denominator? That's not a polynomial, that's natural log of something. And number 2, that theorem on horizontal asymptotes only applies to x going to infinity or negative infinity. It didn't go to x goes to 1. So, can't use theorem on horizontal asymptotes. It does not apply at all. Can't use direct substitution. If I put a 1 in the numerator, I get what? Natural log of 1 is 0. Put a 1 in the denominator, and I get 0. And that's what makes me think, hey, I might be able to do this with L'Hopital's rule. Is the numerator differentiable close to 1? You know what natural log looks like? Yeah, it is. And x squared minus 1 is differentiable close to 1. Is the derivative going to give me 0 if I let x get close to 1? The derivative is going to be 2x. So if I let x be 1, no, the derivative's not going to be 0. So I think we can use L'Hopital's rule. I'm going to, just to make sure that you and whoever's watching this video 20 years from now knows what I just did. That means by L'Hopital's rule. I know, I made it up. I think I need to patent it. That should be the same thing as the limit as x goes to 1 of, what's the derivative of the numerator? Okay, you took a step further than I did to begin with. I thought natural log of ugly is 1 over ugly times the derivative of the ugly. And if you can clean that up in your head and skip your step, yay. If not, then write it down. What about the derivative of the denominator? Plus 2x. So, as many steps as I need to write down to get the right answer. That numerator cleans up to be just what? Or 3 over x, right? Over 2x. And then what does that clean up to be? I multiplied it by x over x to clear out the baby fraction. What would I have? Can I evaluate that limit by direct substitution? Hey, maybe all the answers in tonight's homework are 3/2. Maybe L'Hopital says if you can't find it, if you get indeterminate form, the answer is 3/2. Yeah, we wouldn't even need L'Hopital's rule. I mean, it wouldn't be indeterminate form if you always got 3/2. How could I check that the limit of that function as x approaches 1 actually is 3/2? If this was a test, how could I do? You can graph it. Graph this function and trace it as x gets close to 1. See if y is getting close to 3/2. Alright, that's kind of nifty. Nifty. What's the next one I have circled? Number 24. I like that. That's interesting because we don't know what A and B are. But they're constants. Know them if anything. They're just constants we don't know. I do too. Are sine of AX and sine of BX differentiable as x gets close to 0? Yeah, sine's continuous at the origin, that's fine. Is the derivative going to be 0 as x gets close to 0? The derivative of sine bx would be cosine bx times b. Is that derivative going to be 0? You know what? I think that these conditions are easiest to verify not in the order they're given, and I think I may retype this in a different order. The first thing I would check is, are the numerator and denominator both differentiable close to 0? And if they're continuous close to 0, then they're definitely differentiable. And there's no sharp turning point, then they're definitely differentiable. Then I would say, do you get one of the indeterminate forms that L'Hopital's rule can help with? Yeah. If you let x be 0, then sine of 0 is 0, and then the denominator sine of 0 is 0. So yes, it's one of the forms L'Hopital's rule can help with. So let's just go ahead and take the derivative of the numerator and denominator. And then while I'm looking at it, I can verify the other condition that the denominator is no longer 0. Derivative of sine AX, derivative of sine ugly is cosine ugly times the derivative of the ugly. Same thing in the denominator. Derivative of sine ugly is cosine ugly. Derivative of the denominator. Or, I'm sorry, derivative of the ugly. Now, looking at the derivative of the denominator, I can say, is that 0 anymore? No. Cosine of 0 is 1. So I've verified the third condition. The fourth condition is just, well, does that limit exist? If you let x be 0, what do you have now? Yeah. You have a times 1 over b times 1. That's just a over b. Some constant we don't know. Maybe it's 3/2. All right. Let's look at number 30 and figure out whether we would actually have to use L'Hopital's rule. See if we can anticipate what the answer is going to be and maybe verify it with L'Hopital's rule. Limits at infinity. Can you squint and tell me what you think is happening with that fraction as x gets infinitely big? Tell me what you think.
But the numerator is to infinity, so it's
Mm-hmm.
probably.
I was following you right up until you said it's got to be infinity, and then I'm not sure what your rationale for saying it has to be infinity is. Because exponential functions get big faster than polynomial functions. Yes. Yes, it would. So what do you think the limit is? But the infinity in the numerator is bigger than the infinity in the denominator. It's negative infinity. I think it's going to be negative infinity. If the top of a fraction is getting big faster than the bottom, they're both getting infinitely big, but the top's getting big faster than the bottom, then there's not going to be a limit. The whole thing's going to infinity, except for the fact that the denominator is going to a negative number. So I think the whole thing's negative infinity. Now, the question is, do I feel confident enough in that just to write it down as the answer on a test, or would I like to verify it by L'Hopital's rule? I would like to verify it by L'Hopital's rule, and then because it's worth 30 problems on the test, I'd like to verify it by graphing. It's not going to be 30 points on the test. L'Hopital's rule. What is the derivative of e to the x squared? E to the same old ugly derivative of the other. What's the derivative of 1 minus x cubed? 3x squared. What does that simplify to? What cancel the x squared. So it can't. What does that simplify to? And that's almost as, I can't use indeterminate. It's almost as wonky as original. But, I mean, if I couldn't tell that the original function was going to negative infinity, how can I tell this one's going to negative infinity? I could graph it, or I could use L'Hopital's rule again. Now, what we're saying is, I wouldn't have used L'Hopital's rule on this. I can see that it's going to be going to negative infinity. But if we can't, or if some mean teacher says you must show your work, okay, fine. Then what happens if I take the derivative again? The derivative of the numerator would be what? 4x e to the x squared, and the denominator, the denominator is now a constant. Now I'm feeling very confident that if the numerator is going to infinity, and I'm dividing that by -3, what are my y's really doing? Yeah, infinitely small. That's why if you have an exponential function over any polynomial function, if you differentiate it long enough, it's going to get down to a constant, right? But as long as you're differentiating an exponential function, it's still always going to be an exponential function. So at some point, after however many derivatives, you're going to have an exponential over a constant, and an exponential over a constant is always going to be infinity, or negative infinity, depending on the sign of the constant. Okay? It is pretty cool. And then we could look at the graph, and my y's should be getting smaller and smaller as my x's get bigger and bigger. All right, only have time for one more. Just because it's weird looking, let's do 42. And homework, you go through 41. It's a one-sided limit. Limit as x goes to 1 from the right. And you just won't believe what's in the numerator. Yeah. Why? Do you have any idea? Does that just make you tired looking at it? Yes, say it, Cheryl. Well, let's try to evaluate that integral.
Oh, wait, no, that's definitely.
Okay. So what is the antiderivative, the indefinite integral of cosine theta d theta? Okay. And then I would need to evaluate that from 1 to x. And I'm not doing anything with the denominator right now. 15 plus intentional. What is that numerator if I evaluate it using the fundamental theorem of calculus? Sine of x minus sine of 1. It's not sine of pi, it's sine of 1 over x minus 1. I'm sorry. If I cancel the x's and cancel the dashes and cancel the 1, I just have sin minus sin is no sin.
Factor out the sin. And you get x minus 1 and then you can cancel it. I just
love
remember
it.
last week's degree.
You did. Could we use direct substitution now? In the numerator, we'd have sine of 1 minus sine of 1. That's 0. In the denominator, we'd have 0. So, no, we can't use direct substitution, but we do have the form that works, but L'Hopital helps with. So, by L'Hopital's rule, limit as x goes to 1 from the right of the derivative of the numerator is what? Cosine x. Derivative of the second term is a constant, so it's just 0. And then the derivative of the denominator is 1. What's the limit as x approaches 1 from any side of cosine 1? Well, it's an irrational number, but it's cosine 1. And it's hard to, I would be like you and easily fall into the trap of thinking, oh, cosine of 1 is, and then I realize, oh, that's a pi. Yeah, this is not cosine of pi, this is cosine of 1. All right. 7 through 41. Not bad. Not bad. The medical term for L'Hopital's rule, df dx over dg dx is e, because all drugs end in azine. It is fun. All right. Go to college algebra and do the rational zeros theorem. Yay! You're lucky. YouTube. Complete. I wonder why. Look how that looks different than the others, Miss Emma. What's that? I'm not sure what's fixing to happen. I don't know. We won't know until it finishes and we check it. Put in my 1920 playlist and publish when we're finished, and we'll just see what happens after that.